Okay, so we're going to go back and pick it up at the beginning of section 4.2, and that is our discussion about area. Okay, so the computer is warning me to watch out for sound. I guess I'm not sure why, but there it is. Anyway, so we're going to look at area now. We started this chapter or this section the other day, but we're going to pick it up right here again um, because it's been a couple of days and we want to remind ourselves what this section is all about. So we started out with sigma notation, which we've seen before, but let's just quickly review it one more time. And of course, the summation operator sigma tells us to add up a sum of numbers. All right. So this actually is the uppercase Greek letter sigma. And we often see it associated with an index of some kind. For example, I equals 1 to n, which means we're starting with the number 1, and then we're going to increase it one at a time up until we get to n, whatever number n happens to be. And so you see this kind of notation used quite frequently in calculus and in other disciplines, especially statistics. We see it quite often. So here they're just giving us a quick, simple example. By the way, I did notice there are one or two errors in these slides. We have to keep our eyes open. Here's one right here. So whatever A is, it's some variable or other indexed by the letter I. So that means what we're being told to do here is add up A1 plus A2 plus A3 all the way out to AN. Okay, so now this little strange L here, I think I know why this is here because what happens sometimes is when you have symbols, especially with PowerPoint for some reason, that was supposed to be an ellipsis. Um, if this was published with a PC, let's say, and you try to look at it on a Mac or vice versa, sometimes symbols don't translate properly. And so that's why you run into this kind of thing. I see this all the time because I switch back and forth between Macs and PCs, but you may not have seen this before. The way to get around this is to take the original document and turn it into PDF. But anyway, so we'll probably run into these again as we go along. Now, the I is sometimes known as the index of summation or just plain index. This is what tells us how to proceed to the next term. AI is the ith term. And we have upper and lower bounds of summation are 1 and n. And of course, n is the upper bound. Now, I do want to point out that this summation operator can be used in more general ways. For example, the index doesn't necessarily have to go up by 1 at a time, but if it doesn't, then there's other information that has to be given to you. There's symbols that we could use to represent the fact that you might be going up 2 at a time, for example. But if it doesn't say otherwise, you can assume that we're increasing 1 at a time. So we go, in this case, 1, 2, 3, up to n. And sometimes these are used to represent infinite sums. And if that's the case, then the number on top would be infinity. And also, I do want to point out that we don't have to start at 1. Okay, it's not unusual to start at 0. For certain applications, it makes more sense to start at 0. But, it could be literally anything. But we do know that for the most part, it's going to be an integer. And even then, it doesn't have to be an integer, but that's normally how it's done. All right. Anyway, so then here they're reminding us. Now, part of the reason why they're doing this with us is because there's some nice formulas coming up that will make things a little simpler for us down the road that involve the summation operator. So, for example, here we have I equals 1 to 6. For I, it's literally just the sum of the first six integers. The one directly below it, you notice how it starts at 0. See what they've done? They did this on purpose. Now we're adding up I plus 1, and that means that we have the same numbers, okay? Down here, what they've done is they've just used J instead of I. And, normally we use for an index like this, um, sometimes we use I, sometimes we see J, and sometimes we use K. They're often used as an index. Okay. It's not that other letters aren't possible, but those are the ones you normally see. And by the way, here's an interesting fun fact. The plural of index is actually indices. Now, if you say indexes, that's not, I guess, not wrong, but technically they're known as indices. All right. So with all that being said, so with this case, for example, you notice how J is squared. We can have any function we want here. So we're starting at 3, going up to 7. So we have 3 squared plus 4 squared plus 5 squared plus 6 squared plus 7 squared. Okay, great. Now we get to some messy ones. For D, we have J equals 1 to 5, 1 over radical J, and you can see how that turns out. And oh, here we go. Here's K. And we have 1 over N. Now, N is a constant. It's the largest value that we'll see in our index. It's the K that's going to change from one step to the next. Do you notice how each one of these is 1 over N? That is not changing. Um, it's the K that is changing. So, for example, you can see how they've got 1 squared plus 1, 2 squared plus 1, 3. Okay, now this should have been 3 dots. Also, I just realized too, this should have been K squared. Okay. All right. Well, anyway, now this last one, it's a little bit more abstract. You've got f of xi, a function of some xi, and delta x is, as you know, a small change in x. And so you can see how that turns out. F of x1 delta x plus f of x2 delta x. And again, there's that crummy L all the way out to xn. We're going to need this notation quite a bit in this chapter, by the way. All right, now we need to know the algebraic properties of summation, the summation operator. They're very straightforward. For example, here, this k is assumed to be a constant, and so we can simply factor it out if we need to from the summation operator. Here we've got a sum or difference of two sequences, and so we can break it up into a sum or difference of the two individual sums. So, for example, just make one up real fast. Oh, let's try. Let's just say that. Let's just start at the beginning. Let's say A1 is. Let's say A1 is 1, A2 is 1, 2, A3 is 3, and then let's say B1 is 4, B2 is 5, and B3 is 6. So we'll just keep it simple. So what they're saying here is this. What you can do, and you could add them up like this. That would work. And, since there's only three elements in each sequence, it's it wouldn't take that long. And then what would you end up with? 5 plus 7 plus 9, which is 21. But what they're saying is that what you could have done instead, if it makes more sense, would be to add them up separately. So in other words, what you'd actually have here is A1 plus A2 plus A3 plus B1 plus B2 plus B3. And remember, these values are 1, 2, 3, and 4, 5, 6. So you would end up with 6 plus 15, and of course, it's still 21. And they also would like you to notice that the same thing would be true for differences. So they summarize them both by writing it like this. Okay, so if it's, of course, if it's the sum, use the plus, otherwise you use minus. Okay, a couple of others. Now these are the fun ones. We're going to need these from time to time. So just be aware that these are here. This is slide 9, 4.2. This is slide 4.2. So there's going to be times when this will be very helpful to have this maybe even printed out, have it written down somewhere so in case we need it. So what they're showing us here is the sum of I equals 1 to n, I squared and I cubed can be reduced to something very straightforward. And of course, the sum of a constant is simply n times c. All right, keep an eye on those. Now, here, just to get a little more practice, they want you to take a look at this one. All right, so now keep in mind, what we could do is break this up into two terms. Probably this is what we should do. Now, how does this help us? Because that n is a constant, can factor it out. Well, that's going to look strange. I think I'll just leave this one the way it is because it is a constant. So this one I'll just leave it. And as we just saw, we do have a formula for the sum of I from 1 to n, which is n plus 1 over 2. All right, n plus 1 over 2. Now, the constant, whatever the constant is, we multiply it by n, okay, as you can see right here. All right, so we're going to have, all right, now we're going to need to simplify a little. So these drop out, and this reduces to 1 over n. And so whatever n is, we can plug it in now and we're all set. Now they want us to start with n equals 10. Then the sum of this expression is So that's, what is that, 5.5 plus zero point 0.1, 5.6. Okay. And so they're all going to work the same way. We don't need to do all of them. All right. Now area. Now, okay. Well, we've seen these before. What the purpose of this section is to say, listen, everybody remembers the area of a triangle, 1/2 base times height. But sometimes we have shapes that are tricky to calculate the area of, but they're composed of a series of triangles. So you may be able to come up with a formula by rewriting the shape as as a sum of triangles. Okay. So I think this is what we're leading up to, because what we're going to do is something similar to this with rectangles. So we're not going to need these shapes right now. Anyway, here's an example of what we're going to do. We've got a curve, and what do we want to know? Well, we're trying to find out the area under that curve between 2 points, which are 0 and 2. So in other words, the function is right there. Okay. So it's the function negative x squared plus 5 over the interval 0, comma 2, including both endpoints. Okay. So what they've decided to do here is break this up into 5 rectangles. And because there's 5 rectangles, while the heights are different, each has a base or a width of, oops, 2/5. Okay. In other words, now how did I get that? Because I went the endpoints, the entire interval are 0 and 2. If I want to break it up into 5 rectangles, each one must have a width or a base of 2/5. And that's what you're seeing here. Now, what about the heights of those rectangles? Well, this can be accomplished in one of two ways. On the left, you can see that for each rectangle, there's going to be what we're going to call the left endpoint and the right endpoint. Okay. The height is a constant. It's flat. It's right there. Um, so if you notice here, the right endpoint determines the height of the rectangle because we're making sure that it exactly touches the curve. And then we just draw this across to the left-hand point, and those are our 5 rectangles. Okay, so here on the left, we're using the right endpoint to determine the heights of the rectangles. On this side over here, it's the other way around. We're using the left endpoints. Okay. Now, if you notice, in the left-hand side, if we're trying to figure out the area under that curve, we've understated it. On the right-hand side, we've overstated it. So what do we do? Well, we're going to find a compromise, and hopefully we'll be able to set it up so that the area of the rectangles exactly matches what's going on under that curve. That's what we're aiming for. Okay. And yeah, so this is what they're telling us here. So if the height is being determined by that would be this case over here on the left here. Whereas over here, of course, it's the other way around. The heights are taken from the left endpoint. All right, so for this case on the left, we can actually calculate the areas of those rectangles in the following way. First of all, you'll recall that the area of a rectangle is very simply the product of the height times the width or base. So for these rectangles, the heights remember the heights were chosen to match the curve. Now that's I'm just writing that in. It's a very informal way of expressing what we're about to do. The function or the height of the curve itself at that right endpoint for each one, and they're all different, of course, times the width. The width is not different. In this case, the widths are always 2/5. So the function itself, remember, is negative x squared plus 5. And the right endpoints are, as they showed you in the diagram before, 2/5, 4/5, 6/5, 8/5, and 10/5. So in order to do this, and you can see how this could take a while, the total area of the rectangles is going to be, and we literally just have to go through the whole list. Now you can see this is going to take a while. Unless we can come up with a more clever strategy, maybe we can. Okay. What could that other strategy be? Well, in this case, it doesn't appear that there is one. Well, actually, what would end up happening is you see how you have 2i squared there? What you would have to do is rearrange this so that somewhere in here you have one of these special formulas, this one. Yeah, you would take advantage of this formula, and all of a sudden you wouldn't have such a huge amount of calculations to do. But they're just illustrating this for us. So they've done all the work for us, and we can go ahead and see that they ended up with 6.48. All right, we'll take their word for now. Now, if they do the same thing with the left endpoints, what will be different is that they will be 0, 2/5, 4/5, 6/5, and 8/5. Okay, so you're doing the same thing with those terms, and and again, they've done all the work for us, and you can see it ends up being 8.08. So clearly the true area under that curve is somewhere in between 648 and 8.08. Okay. Now, how do we find the actual area? Well, here's where our friend limit comes into play because the strategy is going to be this. If we, now you notice how we arbitrarily chose five rectangles. If we increase the number of rectangles, the area of the rectangles will get closer to the true area under this curve, or any curve for that matter. So you can see where this is going. In the limit, as the number of rectangles approaches infinity, the area of the rectangles converges to the area under the curve. Not only that, but this is true for both setups, the left endpoints and the right endpoints. Um, both the left endpoint approach and the right endpoint approach will converge to the true area in the limit. Okay, so in other words, they're both converging from the two sides. The left and the left endpoint approach and the right are both approaching from opposite directions. But in the limit, they'll both equal each other, and they'll both in turn equal the area under this curve. So we're going to need a lot of limits in this section. Okay, now here's a curve, um, just some random curve. We don't even know what the function is. And the interval of interest is, let's see, what are we doing here? You know what? I'm going to start all over again. This looks like a mess. Hold on. All right, so we're interested in finding out the area under this curve down to the x-axis, that is, between the endpoints A and B. Okay, so find the area of f of x over the interval, the closed interval, that is A to B. How do we do that? So we're going to pick a rectangle. Yeah, I don't think I drew this as well as I could have. Yeah, because they've exaggerated it to a certain degree. I might have to draw this again, just because this is not really. Let's fix this so that it's super obvious what we're trying to do. Yeah, that's better. Okay. So what they want us to do is pick this rectangle, and the base, or width is always delta x. Okay, that will be determined by how many rectangles we choose. Um, and of course the width of the interval itself. Now they're going to introduce some new notation here. For this rectangle, the lowest value is going to be defined as um, lowercase m. Okay, they're using lowercase m. Let's go find their first definition of it as the, oh, wait a minute now. Oh, I may have to draw this thing again. Well, maybe not. Let's see. Um, all that needs to be, see, they're not, I think what they want us to see here is that this f of lowercase m is the shortest part of this rectangle that touches the curve. Okay. And then, of course, there's also a corresponding tallest part, f of capital M. So let's make a note of these. Okay. And of course, both of them touch the curve. One of them is basically the height of the rectangle, the smallest part of the rectangle that touches the curve. The other is the height of the largest that touches the curve. And what they want us to do, and oh, by the way, the delta x is defined in the following way. We're just taking the difference between the two endpoints and dividing by the number of rectangles. So that's basically a choice variable. We can decide how many rectangles to have. All right, so with all this being said, um, since we're going to have an endpoints for each of these rectangles that we choose. Um, if we start with what they're going to call x0, we have a plus 0 delta x. That would be the extreme left endpoint of the first rectangle. And that would be, let's say here. And then there'll be another one. Wow, this is not easy to draw. Oh, jeez. Let me get that a little straighter. Nope. All right, that's a reasonable approximation, I think. Looks like I got six rectangles. All right, that'll have to do. Okay, anyway, so what they're trying to do is identify the endpoints. The one on the far left, oops, is called x0, they're going to call it. But really what it is a plus 0 delta x's, meaning it's the extreme left endpoint. This is x1, and it is delta x to the right of x0. So in other words, that's what all this is saying, that each one of these is separated by delta x. And in this case, it would be x6. Okay. And then, of course, within each interval, there's going to be f of lowercase m I and f of uppercase m. And that means that depending on the rectangle, there's going to be a largest value and a smallest. Okay. So for each rectangle, the larger side, I guess we'll call it, or I should say taller. That would be even better. And the shorter is f of lowercase mi. The I represents the rectangles. All right, now I don't want to start adding more to this detail to this graph. It's getting pretty complicated as it is, but I guess um like maybe here, you can think of that as f of capital M6, and this would be f of lowercase m6. All right, anyway, so what they're telling us here um, is, oh, by the way, this is something I was looking for earlier. I knew there was an English word for this. When we have these rectangles in here that are all smaller than the curve, these are said to be inscribed. And over here on the right, if you see this terminology, this is what they're talking about, circumscribed rectangles. And so anyway, what you're seeing here, let's copy this into the notes. Oops, that's better. So in other words, for each of these rectangles, the height, and if you, the area of this is f of mi delta x. If you're looking at the entire the height of the rectangle, now if you're only interested in the area under the curve, in other words, if you have your circumscribed rectangles, I'm trying to visualize how I would draw that. It has to be under the curve. It can't be reaching above. Well, anyway, what they're getting at here is this. Um, these rectangles are the ones that are under the curve. These are the ones that are above the curve. Clearly, the area that rectangles under the curve are less than ones that are taller than the curve, and this will never change. Okay, so in other words, if you compare these two, clearly whatever's going on the left-hand side is going to be a smaller total area than on the right-hand side. That's really all this thing is telling us. Anyway, so soon enough we'll be having getting our limits. They're going to define because we're going to see how we'll be able to use this later on. Two sums, which are called the lower sum and the upper sum. And so if you were to add up only the shorter sides of these rectangles, you'd get the SN, lower n. The taller sides add up to capital S of n. So we got to keep an eye on that because it's very hard to see the difference between lowercase n, s rather. They probably should have picked something else, but they want the letter S for sum. And so that's what they stand for. N is the number of rectangles, of course. All right. So that's there so that we can use this as a shortcut. And yeah, so let's look at this case. So, we're obviously trying to find this area here. On the left-hand side. Now, you notice how it says S, lowercase s of n, to refer to the sum of these rectangles. Over here, it's capital S of n. So remember, they're calling that the lower and the upper sum. Okay. And so they're basically telling us that no matter what function we're looking at, the actual area is bounded between these two sums. Okay. All right, good. And so they're going to give us an example here, f of x equals x squared. And they would like us to examine it between 0 and 2. Now, of course, this is a parabola, but they're only interested in this area here. And they want us to break this up into n intervals. So each rectangle will have a base or width of 2 over n, depending on how many rectangles we choose. And there we go. So this is what it would look like. So they've chosen 4 rectangles. And reminding us that the inscribed rectangles on the left, the area will be less than the actual area. And on the right, the circumscribed rectangles will be larger. Okay. So each one of these has a width of 1/2. The left endpoints can be described in the following way. Which, by the way, the actual numerical values here of the left endpoints would be 0, 1/2, 1, and 3/2. Over here, it would be 1/2, 1, 3/2, and 2. Okay. So this is the general formula. 0. On this side, we have and they would like us to see that based on those formulas I showed you earlier, these can be simplified to 2 times. Oh, actually, they're not even using the formulas. They're just taking advantage of the fact that there's a 0 here. And this is, wow, what do you know? That was easier than I thought. Okay, so those are my left end points. Right end points. Okay, so now the lower sum is the sum of, now remember, we're just adding up the areas of the rectangles. If we use the left end points, which is what we're doing here, that's what the lower sum means. We're going to have the sum for all the rectangles, the height, and the base is what we're going to call delta x. But I think we already determined, yeah, the width is 1/2 in this example. So what they've done is, here we go. Uh-huh. Now remember too, f of x is x squared. Mi is 2I minus 1 over n, which means, and delta x, um, they're using the general expression is 2 over n, although we know that it's 1/2, but still, it's 2 over n. And then they've used our special formulas, although they didn't show you all the intermediate steps, I must say, to reduce it to this. So therefore, the sum of all the rectangles is just the sum of what you're seeing here. Okay. Now, how does that help? Well, now they're going to use our special formulas. They're going to break this up. And if you notice, what they're doing is they're going out of their way to find if it's possible to have the sum of I squared and the sum of I and a constant, because we know how to handle those. So we already know how to do this. So we're going to jump ahead, and algebraically, all this reduces to 8/3 minus 4 over n plus 4 over 3n squared. That's our lower sum. If you did the same thing with the upper sum, you'd end up with this. And the only difference is it's 8/3 plus. I'll see if I can make an exaggerated S here. So whatever the actual value of our area under that curve is, it's somewhere between these two. And what they're going to do here is show us that if we took the limits, it equals the actual area under the curve. So in other words, in order to find it, what we're going to actually do is take the limit of this expression as n goes to infinity. Okay. Now I see that they didn't actually do it here. Now, of course, once you know the rules of integration, you don't have to mess with any of this. What you're actually doing is taking what's called the definite integral of this area And, one of the rules that we'll review this again as we go along, but one of the rules is the power rule, which tells us that for an expression like this, we have this expression evaluated over the interval from A to B, which means that you're evaluating it at B, and you do it again with A, and then you subtract. So over here, you're going to have 2 cubed over 3 minus 0 cubed over 3, which is 8/3. Okay, well, that actually works out well because if you took the limit of either one of these expressions as n goes to infinity, it'll turn out to be the same thing. Now, if you remember the way this works, you've got n in the denominator. N is going to infinity, which means that the denominator is getting large very quickly. So that means that you actually have 8/3 minus 0 plus 0 because we have n in the denominator. As n goes to infinity, that ratio goes to 0, and we get, what do you know, 8/3. And I would get the same thing up here with the upper sum. What do you know? Everybody agrees that the limit, the area rather, is 8/3. How do you like that? Okay. So, ooh, I see that we're getting a little late on time here. I guess what we can do is stop right here and we'll save this example for next time. We're almost done with this section. This is 4-3, and then 4-4. No, it's not. It's 4-2. Oh my God. All right, 4-3. What are we doing here? They're formally introducing definite integrals to us here. That's what this is for, this section. So we'll go through that fairly quickly. And then, we're this close to being done with our reviewing. Soon enough, we're going to start chapter 7, which is the new content. So don't worry, we'll be done with this part any day now. Probably next time we meet, it'll be the last review session. After that, we can start the new stuff in chapter 7. Okay. I'm sure you'll be happy to hear that. So, all right. Anyway, we'll knock it off right here. And next time we'll pick it up. I'll wrap up this section and then go on to the Riemann sums and then definite integration. And then we can, at some point very soon, go on and start the new content. Okay. And I'll see you then.